Welcome, I'm Professor Sever, and today we are going to look at applications of the derivative. In particular, we're going to review and discuss increasing and decreasing functions and the first derivative test. So this is the celebrated first derivative test. So notice now the hypotheses are very important. Suppose f is a continuous function on an open interval I, which contains the number c. Suppose c is a critical number of f. If f is differentiable on the interval, except possibly at c, then f of c may be classified as follows. Remember, we have just revealed that extreme values occur at critical points. What is this theorem doing? This theorem is basically testing. It's saying, hey, we have a critical point. We can test f of c under those assumptions to determine whether f has a relative minimum or relative maximum there. So let's look at the first condition. Now if f prime changes, and this means from left to right as indicated here in this diagram, if it changes, if it's decreasing on this side, increasing on the other side, remember we already know a sufficient condition for increasing is the derivative to be positive. So if it's decreasing on the left, increasing on the right, this would give us a relative minimum. Similarly, we would say that if f is increasing on the left and then decreasing on the right, we have a relative maximum. Now if the signs don't change, so if it's increasing up to c and then increasing on the other side, as in that saddle point example, then we would say c is neither a relative min or a relative max of the function. Technically we would say the ordered pair f of c. That's what's happening in this graph. Increasing up to the critical point on the left, and then it continues, it being the function, and then the function continues to increase on the right hand side. Therefore we have neither a min nor a max. And of course if the function is decreasing on both sides, decreasing on the left and then continues to decrease on the other side, you would not have a min or a max either. I'm going to go through each of these three conditions in turn with a graphical example to illustrate why the signs are important. So this is just the first case that we had on the prior slide. So visually, we have a relative minimum. Think of f of x equal x squared. It's decreasing on the left, increasing on the right. That produces a relative minimum, and that's what this is saying. If the function decreases on the left-hand side of c, not on the entire domain, just on this open interval. So there's some open interval, say it's from here to here. Now, here, of course, this is an absolute minimum, so of course it's a local minimum, but the idea is there is some interval I on which the function is decreasing on the left, increasing on the right. This would produce a relative minimum. For relative maximum, we see an analogous result. On the left-hand side, it would be rising to the critical point, f of c, as illustrated by a positive derivative. On the other side, the right-hand side, it would be dropping or decreasing, illustrated by a negative derivative. So in the sign chart, which is our fundamental technique, if we see positive on the left, negative on the right. Again, when these conditions are satisfied, it has to be continuous there. We'll see why in a moment. Then we can claim rising, then falling yields a relative max. And for our saddle point cases, here we have again the classic graph of the cubic function, rising on the left, continuing to rise on the right. Each of those two statements are illustrated here in the derivative. The derivative is positive, illustrated by its increasing. On the right hand side, the derivative is positive, the function is increasing, neither a min nor a max. I'm just giving a simple example to illustrate this other case. You could think of minus x cubed as the function, decreasing on the left of my critical point 0, illustrated by negative in the sign chart. Again, continuing to decrease on the right, illustrated by a negative in the sign chart. So we don't have a min or a max at this critical point c. Again, the fundamental technique when you show your work is to take the derivative, find the critical points, complete the first derivative sign chart, and in doing so you would also include discontinuities of the derivative and the original function because you need to determine the signs of the derivative. So let's look at another example. Remember, this is just an introduction to the theorem. In my next video in this series, I will solve more problems. Now, I wanted you to understand that the converse of the first derivative test is not true. Suppose I had a sign chart of the derivative of a function f, namely I had a first derivative sign chart. And in that sign chart, say we had a critical point c, and say that the function was decreasing on the left and increasing on the right. So it's decreasing up to c, increasing on the right. Well, does this give me a relative minimum? Well, let's look at the graph. Here's a function, f of x equal x squared, parabola. Now, with a hole, removable discontinuity. So here's the functional value at 0 at the height of 2, 1, 2. So first off, is 0 a critical point of the function? Is the derivative 0 there? No, because it's not continuous, so therefore it's not differentiable. Since it's not differentiable, 0 is a critical point. So yes, 0 is a critical point of this function. Something critical is happening, namely, you have a discontinuity here. So is 0, 2 a relative min, as one might think the sign chart depicts? The answer is no. Take an open interval, let's say from -1 to 1. And then on that open interval, f of 0, which is 2, is the greatest value. Therefore, on that open interval I, f of 2 is a relative max. So we can see that even though the sign chart has the pattern of a relative min, relative minimum, in fact, we have a relative maximum. How could that happen? Does that contravene our theorem? No. Why? Because f is not continuous at 0. Let's review. Suppose that f is a continuous function on the open interval I, which contains the real number 0. Now it says c, but we're considering 0 in this example. Well, there's the problem right there. This function is not continuous at 0. Therefore, it is not appropriate to apply this theorem. In other words, we can't say, by looking at the sign chart of this derivative, because it's decreasing on the left, increasing on the right, that the function in fact has a relative minimum. Why? Because if there's a jump discontinuity, just as is happening on this example, you would in fact perhaps have a relative max, or perhaps nothing. It could also be none of the above. Now, if I would have moved this dot below, down here, let's say at -1, if this 2 had been -1, or anything less than 0, then f would have in fact had a relative minimum at 0, even though the function was not continuous there. The point is, we could not apply the theorem. So you need to be careful that you make sure that you're dealing with a continuous function, and you're only classifying those c's for which original function f is continuous. Those will be most of the problems that we deal with in this course. Most of the problems we will face will satisfy the hypotheses of the first derivative test. Thank you for watching an introduction to the first derivative test. I'm Professor Sever. Thank you for watching this video production.